It's also important to remember that sometimes distributions are not characterized by a single peak. Some of them may have 2 or 3 or 4 peaks. So Gaussian distribution, a Poisson distribution, a binomial distribution are called unimodal distributions. But occasionally with biological, physical, chemical data sets, you will see 2 modes or 3 modes. 2 modes is called bimodal, 3 modes trimodal, where there are 2 maxima that may exist. Now, I've mentioned different names of distributions. We've learned about the Gaussian distribution. I've mentioned the binomial distribution, the Poisson distribution, the extreme value distribution, which is extreme left or extreme right of a normal Gaussian distribution. There's also standard exponential distributions. The binomial distribution is essentially a polynomial expansion, which allows you to calculate coefficients. It's found in any situation where you can have a true, not true, or binary, plus, minus, 1, 0 type of outcome. So this is why we see it in heads and tails. The coefficients of a polynomial or binomial expansion describe the intensity of the peaks in the curve. So p plus q to the 5th power will produce a polynomial with coefficients of 1, 5, 10, 10, 5, 1. 6 peaks with intensity. As the number n increases, or in essence the number of coin flips that you perform increases, or the number of binary tests you perform, the polynomial or binomial expansion trends more and more towards a Gaussian shape or a Gaussian distribution. And technically the Gaussian distribution is the binomial with the power n going to infinity. Another type of distribution, the Poisson distribution, is described by the curve and the equation given here. It has a mean, but it also involves factorials. And depending on the choice of the mean or mu, you can either have something that looks very much like a Gaussian distribution where the mu equals 10, or you can have an exponential distribution where the mu is 0.1, or between 1 and 3, you'll have the distribution looking like a skewed Gaussian distribution. As I said, the Poisson distribution is found in different circumstances and different physical and biochemical phenomena. The extreme value distribution happens when you sample only the extreme edges of a normal distribution. So if you're taking only the top chess players in the world and evaluating them on their chess performance, you're not going to get a Gaussian distribution in terms of their overall skills. You'll get a fairly skewed distribution that's called an extreme value distribution. You can either take from the very best or the very worst, and either way it'll exhibit some strong skewness. The extreme value distribution is what's used in evaluating the performance of sequence alignments. And so we're using that distribution instead of the Gaussian distribution is critical to assessing the quality of sequence alignments. So a skewed distribution like the extreme value distribution has lots of extreme values that are very far from the mean or the mode. When you have a very skewed exponential or extreme-like distribution, it's really hard to do standard statistical tests like the t-test with this. And it's important to actually develop methods to change the shape of the distribution as much as possible so that it resembles a normal or Gaussian distribution. So that leads us to a discussion on normalization, especially as applied to skewed or distorted asymmetric distributions. In this example, we've got a whole bunch of people, but you'll notice on the right side there are 5 giants. The presence of these 5 giants will skew the distribution in an unusual way, so that the shape of the curve will be shifted with a long tail in terms of height. So a skewed or uneven distribution can be changed into a normal distribution by applying log transformation. That is, taking the log of the data, in this case the heights, and the result is it will bring those highly skewed heights, the ones that are very high, a little closer to the mean. As a result, this skewed distribution becomes more symmetric and it therefore becomes more Gaussian. So here's an example of a skewed distribution on the left. You can see that there's a tail that stretches out to the right. There's a very high peak. It doesn't look very symmetric. On the other hand, if you look at the distribution on the right, this is a normal distribution. And in this case, the data has been logged, or a log has been taken. It could be log base 10, a natural log base 2, doesn't matter. But it'll convert this asymmetric skewed distribution into a symmetric normal distribution. Here's some more examples where we're taking real data measured from, in this case, microarray data. You can see the intensity data is very skewed on the left. We take the log transformation, and the distribution now looks a little more symmetric. It's not perfectly Gaussian, but it's certainly much better than what it was. So the log transformation is a great trick, and it's used almost every day by every statistician. And it's a way of converting naturally skewed or exponentially decaying data into a format that can be processed using standard statistical rules. So normalization essentially allows you to work with standard statistics because most statistical modeling, all the theory behind statistics, has been based on the population having a normal or Gaussian distribution. The basis for t-tests for ANOVA is that the data being tested is fundamentally normal or Gaussian. If it isn't, the theory starts to break down and you can have serious misinterpretation of your data. So rule of thumb, always try to normalize your data in any way you can. Make it look as Gaussian as possible. Now there's another trick that statisticians also use, and this is called scaling. So here we've got two populations, sets of individuals on the top, we'll say that they're from the US, and then another set of individuals in green, we'll say they're from Ireland. Looking at them, you can see that probably on average they're about the same height, same individuals. Maybe the green ones are a little bit shorter. Now, what happens if, in fact, we measure them and the ruler that we're using to measure them has been miscalibrated? In effect, we have some bias in the data or the data measurements, so that the height for the top population, the ones in blue from the US, is 10% higher across the board than the ones that were in green. So through miscalibration, we've introduced a bias. And in essence, now with this set of measurements, we are seeing what to our eyes looks like two very different populations. Yet, when we look at the picture, we can see they're basically the same height. If we scale things properly and either get a better ruler or adjust the measurement, we would find that, in fact, the two heights for the two populations, the blue and the green population, the US and Irish, is pretty much the same, and that the distributions quite tightly overlap. So scaling is a way for correcting either misaligned or mismeasured data, but it's also a way of correcting for data that spans very large units and dimensions. So we can have a situation in metabolomics where you might have metabolites that are all measured at micromolar levels, say certain types of organic acids, versus other compounds like amino acids that are measured in millimolar, or some concentrations of salts and ions that are measured in molar levels. So scaling is not only a way of correcting for mistakes in measurement, it's also a way of correcting rescaling metabolite, gene, or other measurement concentrations values, so they're more comparable. In metabolomics, we can deal with scaling problems introduced by dilution. So urine can easily be diluted if someone has not been drinking for a long time or someone has been drinking a lot. You can seriously dilute the urine by scaling it and dividing the values by the creatinine levels. You can rescale the concentrations so they're comparable. There are other techniques for scaling called min-max scaling, feature scaling, Pareto scaling. All of these allow you to bring units closer together, values into a tighter, more reasonable data set. This is illustrated here where we've got essentially 4 groups of metabolites ranging from concentrations with the yellow-orange up to molar, and then the blue ones perhaps down to micromolar, and everything in between. And these are, literally dozens of different metabolites, but they just happen to be in different categories or different levels of abundance. The fact that they vary so much certainly would mean that you couldn't do standard statistics. This is multimodal data. We want to make it unimodal. And so scaling offers a way of making multimodal data more unimodal. This is shown in an example of a real data set where on the left we have some data measured in urine, I believe. And if you look closely, you might be able to see some of the names of the metabolites. But you can see that certain metabolites, some have very high concentrations. There's about 3 or 4 that are very high concentrations on the left. And then the rest of the metabolites are all tight around a few micromolar. So by rescaling this and applying the appropriate corrections, we can now change this multimodal data set into something that's unimodal. And then by doing some log scaling or log normalization, we can make the whole data set not only unimodal, but also Gaussian or normal. And that's what we see on the right. So we've rescaled the data and also done a little bit of log scaling to convert the data into something that is now Gaussian in its overall shape and distribution. And at this stage, we can start applying standard statistical methods because we have a normal distribution.